Episode 11, Design, Radon. Radon is a colorless, odorless, radioactive gas that occurs naturally in the soil and rocks. It can enter homes and buildings through cracks in the ground, crawl spaces, and basement walls. Radon is the second leading cause of lung cancer in the United States after smoking. When inhaled, radon particles can damage lung tissue and increase the risk of lung cancer over time. This map shows the threat of radon across the continental United States. In Minnesota, all new construction is required to be radon resistant. Radon Mitigation System in vents. The system is installed under the foundation. URL is listed down in the comments section. Radon venting. Gravel. Use a 4-inch layer of clean, coarse gravel below the slab, also called the foundation. Plastic sheeting or vapor retarder. Place heavy-duty plastic sheeting, 6 mil polyethylene, or a vapor retarder on top of the gravel to prevent the soil gases from entering the house. The sheeting also keeps the concrete from clogging the gravel layer when the slab is poured. A vent pipe. Use a 3-inch or 4-inch solid PVC Schedule 40 pipe, like the ones commonly used for plumbing. Run the pipe vertically from the gravel layer, stubbed up when the slab is poured, through the house's conditioned space and through the roof to safely vent radon and other soil gases outside above the house. Although serving a different purpose, this vent pipe is similar to the septic drain waste vents. This pipe should be labeled Radon System. Sealing and caulking. Seal all openings, cracks, and crevices in the concrete foundation floor, including the slab perimeter crack, and walls with polyurethane caulk to prevent radon and other soil gases from entering the home. The installed system is initially passive, but it can be made active with the later addition of a fan. To this end, an electrical junction box with an outlet must be installed in the attic near the radon vent. This will be used later for a vent fan should, after future radon testing, a more robust system be needed. Episode 12, Design, Septic. There are very specific code requirements for number of bathrooms, types of tubs, presence of a food disposal. Our existing system was good, but required a larger septic tank. We simply added another tank to the system. We had an 1,000-gallon tank with a total requirement, though, of 2,250 gallons. We needed a second tank of 1,250 more gallons. Minnesota 7080-1930 Septic Tank Capacity. Subpart 1 Dwellings. The liquid capacity of septic tanks must be at least as large as the liquid capacities given in Table 5. We had 5 bedrooms. Septic tank liquid minimum capacity started with 1,500. Subpart 2 Garbage disposals. If a garbage disposal unit is anticipated or installed in a dwelling, which we were planning to install, the septic tank capacity must be at least 50% greater than that required in Subpart 1 and must include either multiple compartments or multiple tanks. In addition, an effluent screening device is recommended. Subpart 3 Sewage pumping. If sewage is pumped from a sewage ejector or grinder pump from a dwelling to a septic tank, the septic tank capacity must be at least 50% greater than that required in Subpart 1 and must include either multiple compartments or multiple tanks. In addition, an effluent screening device is recommended. These both applied to us. Subpart 4 Sewage pumping and garbage disposals. If conditions in both Subparts 2 and 3 apply to a dwelling, the mitigative requirements of either Subpart 2 or 3 apply. The requirements of both Subparts 2 and 3 need not be additive. We fall under Subpart 4, which combines the septic, garbage disposal, and the sewage pumping. Using Table 5, our original requirement is 1,500 gallons. From Subparts 2 and 3, we need to increase this by 50% to be in compliance. 1,500 times 1.5 equals 2,250. Our total septic tank capacity, therefore, needs to be 2,250 gallons. When designing a septic system, you need to have core samples of the soil, looking for redoximorphic features, commonly referred to as redox features. These are color patterns formed in the soil by the process of reduction, translocation, and oxidation of iron or manganese compounds. The previous property owner had installed a septic system in 1995 with the desire to someday build a house. it had been little used over the years. I had it inspected in 2021 and it failed the redox test. Because of the failure, I was advised to install an above-ground mound system. I then educated myself in septic field soil requirements. I learned the words and what we were looking for, such as redoximorphic features, redox. Again, these show where groundwater has historically come through the soil, leaving horizontal iron trace marks. I challenged the finding in that my neighbor had just installed a septic field not 40 feet from my field, and he had no problem passing his redox inspection. So the inspector and the county representative came back out to my property to reinspect. I was very careful not to challenge their knowledge or process, but simply wanted them to show me why I failed. They went to take a core sample, and I immediately stopped them, asking, "Well, why are you taking this from a low wet section of my property? My septic field is up over there." They then took a core sample to 84 inches deep. There was no evidence of redox until they reached 74 inches deep. The field depth was 72 inches and above, so the absence of redox, the soil, and by extension, the field, passed inspection. There's an additional required test that sees how quickly the soil can absorb water, not too much clay or other impediments to water transfer. This is known as an absorption test or a percolation perk test. My field had no issue passing that test. As per our discussion above, we had the existing 1,000-gallon tank. We needed to add to this a multi-compartment tank of 1,250 gallons with an effluent screening device. Lastly, I needed to size the pipe from the house to the septic tank. Minnesota code states, no building sewer shall be less than 4 inches in diameter. This is the septic piping outside of the house. Definitions. Building drain means that part of the lowest piping of the drainage system, which receives discharge from soil waste and other drainage pipes inside the walls of the building and conveys it to the building sewer beginning at least 1 foot outside of the house. Building sewer means that part of the drainage system which extends from the end of the building drain and conveys the discharge to the public sewer, private sewer, individual sewage disposal system, or other point of disposal. Note, from above, this is 1 foot outside of the foundation. I have several good URLs in the comment sections below. Episode 13, Design. Water supply. We needed to calculate pipe sizes for 2 different areas, the size of the pipe that brings the water into the house and the size of the pipes that distribute the water to the fixtures. We begin by identifying the water supply fixture units, just like drain, waste, and vents. I created this table listing the floor, fixture units, and distance from the fixture from the pressure tank. Because this is a domestic, not industrial installation, we can use a reduction method known as the 75% method. The separate cold water and hot water fixture unit valve for fixtures having both hot and cold water connections shall be permitted to be each taken as 3/4 of the listed total value of the fixture. From my table, you can see that my highest fixture unit is 3.0 and my greatest distance is 70 feet. There are 2 methods of distributing water throughout your house: trunk and branch or home run. Most houses have the trunk and branch, which uses a larger pipe through the house and then a smaller pipe to each fixture. I elected to use the home run method. This method uses a dedicated smaller pipe all the way from the pressure tank to each fixture. Both the hot and cold pipes will be home runs. To accomplish this, I planned on using a manifold like the ManaBlock pictured here. Back to our original table, we can see that 1/2 inch pipe will work on all of my fixtures. I didn't have the 3/4 inch bathtub fill valve. Now that we know our 2 limiting factors, we can size our pipes. Our furthest distance was 70 feet and our highest fixture unit was 3.0. So we enter the table to find a combination that we don't exceed. This is the 80-foot distance and the 4 fixture unit. With our pressure set at 40 psi, we have the following: street service pipe diameter of 3/4 inch, building branches of 1/2 inch. Had we done a trunk and branch, we would have needed to add each of our fixture units, and that would have driven us to 28 units for the cold fixtures. This would have resulted in a much larger 1¼ inch trunk pipe through the house. Other design considerations. Rule of thumb for shower valve placement: tub spout is 4 inches above the top level of the tub. Shower control is 8 to 18 inches above the tub spout. Shower valve is 80 inches above the floor, resulting in a shower head being 65 inches to 78 inches from the tub floor. Shower wall covering. I needed to choose a wall covering for showers. I had used Hardy board in the past, but elected to go with John's Manville Go board. Rule of thumb for toilets. Toilet heights. Toilets come in 2 different rim heights, comfort and standard. We elected to go with the higher comfort toilets. Toilet placement. The toilet flange center cannot be less than 15 inches from any object to the side and is generally 12 inches from the wall. The front of the toilet needs a 21-inch clearance. Toilet flange. The best practice is to install the toilet flange on top of the finished floor. If you install the toilet flange flush with the finished floor, or even below the finished floor, leak paths will form because the flange won't be at the correct height to accept the horn at the bottom of the toilet. Toilet flange on concrete floor, new construction. We use a closet flange. Find the right diameter, don't cut the pipe off flush with the floor. Cut pipe flush with the finished floor, i.e. flush with the top of the tile. Install closet flange. I use the Oatly 3-inch or 4-inch Easy Tap closet flange, PVC with stainless steel ring. It is a 3-inch by 4-inch knockout flange. URLs are below. I elected to use PEX for my water supply lines to my fixtures. You can use PEX A or PEX B. Make a choice and stick with it. The tubes have different manufacturer, different diameters, and different tools for installation. I used PEX B. It uses internal fittings and crimps. I needed 1/2-inch pipe, Type B, PEX. Type A PEX requires an expansion tool as shown here. Type B PEX requires a crimp tool or shark bite. Caution: do not mix potable water PEX with in-floor heat hydronic PEX. Hydronic PEX is made of different material and has an oxygen barrier. It will not work for potable water. The pipe and fittings are different sizes. Water softener. Your water will need some sort of softener and filter system. If you have well water, you may need additional filters to take out impurities. I purchased a Water Boss softener. Considerations if you have a well. You need to shock your well after placing the pump. You need a water analysis of your well to see what might need to be filtered. I had an existing well that was 50 feet deep with a 20-foot static level, and it gave 16 gallons per minute. Inside the house. I used a 22-gallon Flexcon WF7 fiberglass pressure tank with internal bladder. I recommend that you stay away from the other brands that have an internal bag instead of a bladder. They fail fairly often. You'll need a pressure switch. I used a 40-60 pressure switch. I recommend a tank package, T-pack, that has an elbow to move the assembly away from the floor. This is the T-fitting that goes on the front of the tank. Water in, water to tank, water out.